We're going to go ahead and start. Just getting all the right screens up. And there's one that has like a black background, so I turned off the light, so I think it's easier to see now. Okay, so we're going to jump between the notes and this simulation that's linked at the bottom. So go ahead into your Chapter 11 notes, get to this page, and then what I would recommend is open up that simulation and have it in a separate tab, because I'm going to go back and forth quite a bit, okay? And I realized in my last class I'm going to do a lot of silly gymnastic-y looking somethings. I was never, a cheerleader, so please excuse it, but it seems to be very helpful to stick the shapes in people's minds because they can look at me and think how hilarious I looked, and then they remember it. Okay, all for the good of you guys. All right, so we are moving on from talking about the two-dimensional representation that Lewis structures give us to talking about how these molecules look in real life. And the reason why we care so much is because the shape of something has a huge impact on how it's going to act in nature. So lots of you guys are biology students, so think of enzymes as like the perfect example of this, right? The enzymes have to have, the protein has to have certain interactions in the protein to make it the right shape to fit perfectly into the receptor. And if it's not going to do its job. Okay, so at a very basic level, we're looking at shape that would translate into shape of much bigger molecules as well. Okay, all right, so all of the steps that are written here, I'm going to go through them as we talk, but I'm not going to refer back to step number 4, do this. This is kind of your reference point for when you're doing practice problems on your own, that you can kind of come make sure, did I miss anything? Is there something else I'm supposed to be doing? And kind of use that as you're going through. Okay, and then like I mentioned, this simulation is going to be really helpful, particularly, today in class, but when you're doing it on your own as well. So whatever you need to do, if you want to just keep this tab open so that as you're working, you have that to refer back to, would be good. Okay, so we are going to start. I'm going to give us a couple examples on each one of these. It says 2 groups, 3 groups, 4 groups. From my understanding of what you guys are doing in lab, you've seen a lot of this already. I think the way that your lab instructors are talking about it is this weird AXE. Does this sound familiar? Okay, all we're talking about is X is how many atoms there are surrounding that middle. I think this is what the reference is. The A is the middle atom. And then X and E are the atoms that are surrounding it and the lone pairs that are surrounding it, okay? So if you need to connect this back to lab, or for that matter, if you're confused by what's going on in lab, this might be helpful for that, okay? So we're gonna start with examples that have 2 groups, meaning either 2, in this example, we're just gonna do 2 atoms. So we're gonna have a middle atom with 2 atoms on the outside, no lone pairs. So we've done this one already, but I want you to draw the Lewis structure of BeF2. I also want you to do CO2 and then HCN, okay? So 3 different examples, all of which are gonna have a central atom with 2 atoms on the outside. Okay, so take a minute or 2 and work through that. Okay, so I'm going to go ahead and draw these on. Just double check that you have the same structure. So everything in this chapter is reliant on drawing good Lewis structures. If you have the wrong Lewis structure to start, you won't be able to get the right answer. So a couple things that you can do if you're struggling at all with chapter 10 is obviously make sure you finish the homework. So it was of 72 people, 8 people didn't finish it last night, and as well as 8 people didn't finish the pre-class assignment. So if you're like, oh shit, I was one of those people. So you can still do it today. It's like a 10% off per day deduction on those. Now the homework, I think you have to email me and tell me that you went ahead and finished it. It's just a dumb system and I have to go in and manually do it, okay? But if that happened, go ahead and do it as soon as possible. As long as it's before midnight tonight, it's just gonna be 10% off. And then that was the one thing. Then the next thing you could do to make sure you're good with chapter 10 is take the first attempt at the chapter 10 practice exam. So the actual exam is February 13th. So it's, I don't know, a couple Fridays from now or a week from this coming Friday. So like 2 weeks away. So you have these 2 practice exams that are going to count for grades. And the best way to utilize them is to do the chapter 10 one now, do the first pass at it. It'll help you feel confident that you're ready to move on to 11, maybe isolate a couple things you still need to study, then wait until closer to the test time and use the second attempt as a way to study and make sure, review the material, okay? And then between those 2 attempts, whichever grade is higher is the one that it'll take. Okay, 11's a little harder because they're going to be in close succession, but that's the way to use that first one. Okay, so back to drawing good Lewis structures. This is what you should have for each of these 3 molecules. So key point to recognize here is that we are going to look at the central atom when we're doing these problems. So yes, it's important to draw fluorine with its 3 lone pairs, but I don't really care about the external atoms right now, or the peripheral atoms. I'm going to focus in on the central atom and what exactly is surrounding it, okay? So in each of these examples, there are 2 electron groups surrounding the central atom. So if you look back at your 1, 2, 3, 4, 5 steps, it says, I'll just go back there for a second. It's on number 2, it says count the electron groups surrounding the central atom. An electron group can be a single bond, it can be a lone pair of electrons, or it can be a double bond or a triple bond. Double bonds and triple bonds count as 1 electron group because they take up the same physical space. Okay, so you guys ready for me to do my dance moves? So my head is C, okay, and my legs, my feet are H, okay, they're bonded, and then this is my N. I'm trying to remember what the molecule was. HCN, okay? So there's 3 bonds here. I don't have 3 arms, but pretend that you have 3 arms here. They're still taking up the same physical space as the 1 bond to hydrogen, okay? So it doesn't matter if it's a triple bond or a single bond, they're gonna behave physically like they take up the same amount of room. So when we look at these groups, beryllium has 1, 2 groups surrounding it. CO2 has 1, 2 groups surrounding it. And HCN, that carbon, has 1, 2 groups surrounding it. Okay? Now I haven't done any that have lone pairs on the central atom, because again, that's what we care about is the central atom. When we get to 3 groups, I'll do some of those examples where there's lone pairs on the central atom. So all 3 of these are going to look just like I had, okay? So 1 in the middle, 1 up top, 1 down bottom, and guess what? These are electrons. And if you remember from Chem 1, I probably said it 25 times, everything in chemistry boils down to positive and negative attracting, negative and negative repelling, and positive repelling, okay? Repulsion and attraction, that's everything in chemistry. So here, where we see that is the repulsion of electron groups. So if I've got one set of electron groups here and one set here, and they're all negative, if I try to squeeze them closer, like that's no good, right? They're gonna start repelling, so they go back straight away from each other, as far away from each other as possible. Same thing, if they start getting close, nope, they repel. This is the shape that they would take to be as far away from each other as possible. Okay, so it's a line, it's 180 degrees between the two bonds. Keep ending up with highlighter, there we go. And they will just be in a straight line. It's very uninteresting. Okay, let's look at this in the simulation just to see how the simulation works. Okay, so there's beryllium, purple, 2 fluorines in the white. They're in a straight line. Fascinating. Okay, if I change one of those bonds, so you'll notice down here, this says model and real molecules. We want to start with the model almost every time when we're doing this, because then we get to customize how the bonds look. So if we're doing CO2 that has 2 double bonds, no singles, I'm going to get rid of those single bonds and add double bonds in. And then it's immediately going to push those electron pairs however they're naturally going to arrange so that they have as much room as possible, so that they're not repelling. Okay? I mentioned that the bond angles were 120 degrees. That's just, a straight line is 120 degrees. So if you click over on options where it says show bond angles, it's going to tell you what that angle is. That's going to be an important piece of information that we have to talk about when we're talking about these shapes. And then the other thing that's going to be important are these 2 types of names of the shape. So for right now, we're just going to start with electron geometry. So I'm going to click that on. It says it's linear. So it's not a hard name to memorize. It's in a straight line. We call it linear. And what that electron geometry is telling us the shape that the electron pairs take on. So how do those electron groups push away from each other? In this case, they push away the straight line. I can do the single and triple bond as well. So single and triple, and you see it behaves just the same way, okay? It's still linear, it's still 180 degrees away. Okay, good with this so far? Let's do a little bit more complicated ones. Okay, for the 3 group example, I want us to do BF3 and what was the other one I used? O3, which is ozone. Okay, I want you to do those 2 Lewis structures. Ozone might take you a little bit of messing around with it, but that's good. It's just practice for chapter 10. And see what you can get out of those 2, and then we'll talk through those. So just a hint on O3, they're all in a straight line don't try to make it a triangle. Things don't start turning into like rings or circles until you've got at least 5 atoms. It's just too squished.
What molecular geometry was HCl?
Linear. All 3 of those were linear.
Okay.
Yeah. Oh, molecular geometry. We haven't gotten there yet. Electron geometry was linear.
Oh, it's electron.
Yeah.
I always get this confused.
I know. Well, I'm going to clarify it on this one because on the last one, there's no difference. So on this example with 3, we'll talk about when does it change.
Yeah, I meant electron geometry.
Oh, okay, good. Yep. Okay, so let's look at O3 together if you haven't finished yet. So they each have six valence electrons. We need to start by actually bonding them together, okay? And then we're like, well, wait, there's those 2 lone electrons on the 2 outer ones. Like, those can't bond. How do we do this? The only way to really handle it is to move one of these electrons to make a pair on the one that's on the far right, and then bond these into a double bond. So it looks like lone pair on the central atom, single bond, 3 lone pairs on the far right, and then double bond and 2 lone pairs on the left, or vice versa. You know, a mirror image of that is fine. Technically, this would have another resonance structure, which would have a bond order of 1.5. Just kind of reminding you of these chapter 10 things. And now let's look and make sure everything has 3 groups, like we said. So BF3, those 3 groups are all single bonds. Okay, 1, 2, 3. For the O3, we're looking at this oxygen in the middle and the groups that surround it. So there's a single bond, there's a double bond that counts as 1, and then there's a lone pair. So still 3 groups, just a different type of 3 groups. Okay, so we're gonna go take those 2 ideas over to the simulation. So if you wanna keep your notes open so you can refer back to it, that's fine. Okay, so I'm gonna do the first one, which was 3 single bonds. So first thing you notice when you kind of rotate this shape is that they're all in a plane. So when things could be drawn 2-dimensionally and still look right, we would call that planar. So there's nothing in the z-axis here. Like if this is the xy axis, there's nothing in the z-axis, okay? So conveniently, because of that planar, there's 3 things. So we call the electron geometry trigonal planar. It arranges itself in a plane, and there's 3 of those things in that plane. So this would be this, right? Is that about 120? Like that, okay? So I'm the boron, fluorines are out here. If I tried to push them closer, like a T, now these guys are too close to that other electron pair, so they push back out. If I tried to push these closer, now they're too close. So like the optimum is 120 degrees separating everything. Okay, so you'll definitely have questions like, here's this molecule, here's BF3 or BCl3, whatever I said this was. What's the electron geometry, okay? So the way you approach that is you draw the Lewis structure, you count up how many electron groups are surrounding it. And then you think, okay, if there's 3 groups, what does it look like? Oh, right, that's called trigonal planar. Now, the step that a lot of people try to skip is they try to memorize 3 groups, trigonal planar, 4 groups, tetrahedral, 5 groups, trigonal bipyramidal. It gets really complicated to try to just straight memorize that, okay? The looking at the simulation, remembering the funny different shapes that I'm going to make with my body today, that's what's going to help you remember the name, okay? So the other thing is there's another concept that I think you guys have started talking about in lab as well, of molecular polarity. So we talked about bond polarity. We have to also talk about molecular polarity. That is going to be impossible to predict if you can't picture the shape of the molecule in 3 dimensions, okay? So whatever you need to do to start picturing that, the simulation is probably the easiest way to do that. We used to use models, like little plastic models, when I was in school. Those are fine. There are definitely some limitations, and this is just as good and faster. So I kind of stopped bringing them to class a couple of years ago. Okay, what about if one of those is a lone pair? So that's what we got to do next. We're going to take off one of these bonds and put a lone pair. So this would be O3. Okay, so I'm going to say the exact same shape, but now, I guess I should have rotated that, but now one of these things is a lone pair, okay? My bond is still approximately, we'll get to that in a second, the bond between this atom and that atom, you know, the 3 that connect, that's still 120 degrees. Why? Why doesn't it just go up and down? Because there's still 2 bonds. Because I still have an electron pair over here pushing everything out so that they're all equally spaced, okay? So the electrons still arrange themselves the same way. We still call that trigonal planar because they're still arranging the electrons in the same way. So this is more aligned with how I was shaping it, okay? Once we have a lone pair on there, the other name we want to talk about is how the atoms are arranged, okay? So yes, the lone pair is there. It has a big influence on the shape, but we want to talk about how do the atoms themselves look? Like if we were to just trace an outline of the atoms, what would their shape be? Because physically, you know, the mass is concentrated in those atoms. So it's important for us to know that as well. I'm about to touch the screen. There. So this is the molecular geometry. So think of this as tracing the shape of the atoms. People will often try to jump from looking at the Lewis structure to molecular geometry. And they're like, oh, it has 2 bonds. It must be linear. No, because I've got this lone pair there that's offsetting that geometry. So the electron geometry is trigonal planar. The molecular geometry is called bent. That's pretty easy to remember, right? It's not straight, it's bent. Okay, quick note on the bond angles. So, yes, we would predict that it's 120 degrees because there's still 3 things that are taking up space. The problem is the lone pairs take up more room than the bonds. So, let's see. I'm going to do this. I'm trying to think how to do this. All right, it's going to be weird now. Okay, ready? This is my lone pair, okay, and these are my 2 bonds. So if this was a bond, it would be stretched out straight because it's going to be attracted to this atom and the one up there, okay? But it's not, it's a lone pair. So it goes like this because these electrons up here are like, we're not being attracted to anything and we're repelling each other, so we're just going to push away a little bit, okay? And they form more this like balloon shape instead of stretched out scape. So when they do that, now you can see my elbows are like a little bit closer to my legs. They're going to start repelling down there. And so there's just this little tiny change in the bond angle to push that angle slightly away. Not a ton, because we don't want to mess with that angle too much. So we space it out evenly because the lone pair takes up a little bit more room. And now when we measure the bond angle, it's like 119. Okay? So it just squishes those bond angles ever so slightly. And you might be like, who cares? It does matter, especially if you get two lone pairs in there. There's like a difference of like maybe 5 degrees, and it might end up impacting something, okay? So we have the predicted bond angle of 120, but once we've got that lone pair on there, it takes up more room and it squishes it down just a little bit. So if you want to write it on your notes, go ahead and write 119. Or what I'm going to expect you to do on an exam is just write less than 120. I don't actually care if you know the exact number because it's going to change depending on what the atoms are, but it's definitely going to be a little bit less than 120. So recapping, for 3 electron groups surrounding a central atom, the electron geometry is called trigonal planar for both of them in this example. For O3, the molecular geometry is called bent, and its angle is slightly less than 120. And we didn't talk about this yet, but in the BF3, the molecular geometry, well, if I'm tracing the atoms, it looks the exact same as the electron pairs, right? So the name doesn't change. It's still trigonal planar. Okay, there is a table that's going to summarize this stuff. So I'm going to show you the table now and kind of show you how you can use it as a reference guide. For the love, please don't try to just memorize the table. Straight memorization, unless you've got like a photographic memory, is not going to hold up to getting you through an exam, okay? This is like a guide to help you remember which name corresponds to which, but the best way to think of it is to visualize what it looks like in 3-dimensional space, okay? So this is the total number of electron groups. And then these two are telling you how many of those are bonds and how many of those are lone pairs. Okay? So the 2 examples we just did were 3 electron groups. If all of them were bonds and no lone pairs, we would say that both the electron geometry and the molecular geometry would be called trigonal planar because the electrons are arranged like this and the bonds are arranged like this. It's the same thing because there's no lone pairs, right? If I have 3 groups, it doesn't matter if they're bonds or lone pairs, the electron geometry is still called trigonal planar. This one's a lone pair, okay, but it's still called trigonal planar because they're still arranged in the same shape. The electrons are, not the bonds, not the atoms, but the electrons are. So this is still called trigonal planar. And the angle, or at least the predicted angle, is always going to be based on how many groups there are. So if there's 3 groups, it's always going to be 120. It's just if there's a lone pair, it's a little bit less than 120. Okay, and then last thing, here's my lone pair. Again, the molecular geometry for this guy, in this case they use SO2, I think, and we used O3. The shape is bent, okay? And the angle is slightly less than 120. Okay, do you guys want to clarify anything? Are we unclear about like different terms at this point or how we figure them out? Yeah.
So
It's okay if you need time to figure out what the question is.
Yeah. I'm trying to figure out how to phrase this. So how do you know when something's the same electron geometry but it's different molecular geometry?
If there's a lone pair. If there's no lone pair on the central atom, the molecular geometry and the electron geometry are the same thing. If there is a lone pair, you want to think about the fact that the lone pair is influencing the shape. Like the lone pair is there, it's taking up room, but there's no atom there. So if I just trace atom, 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 that shape is different than the trigonoplanar shape. So if there's a lone pair, that's when the names will be different.
Is there ever a point in time where there's more than one lone pair?
Yep. Yep. So now we're going to get to groups of 4. So we're going to do same type of thing, but we're going to do 4 groups. So these are the 4 molecules I want you to draw Lewis structures of. They're all going to have 4 groups, but different mix of bonds and lone pairs. Oh, I'll send the roll around. I forgot to do it in my other class, but I'll do it as much as I remember. Oh, it's Groundhog Day. Did anybody remember that? Not that it's, a crucial thing for you to remember, but shocker, 6 more weeks of winter. I'm so surprised. So I'll go ahead and draw these up, and once you guys finish them, just check and make sure you've got the same thing. None of these are particularly complicated, similar to stuff we've done already. I guess I could have kept the trend going here and done OF2 instead of H2O, but oh well. Okay, so double check your structures. So all of these should have 4 groups surrounding the central atom. I'll go ahead and highlight those. So for CF4, it's just those 4 fluorines, so they're all bonds. For NF3, there's 3 bonds surrounding that nitrogen and 1 lone pair. And then for water, surrounding the oxygen, 2 lone pairs and 2 bonds. So maybe just for the sake of noting it, all of them have 4 groups. So we know they're actually all going to have the same electron geometry, like the same name for the electron geometry, because that's just reliant on how many total groups there are. The molecular geometry name is going to be based on how many of them are lone pairs. So this one has 4 bonds. This one has 3 bonds and 1 lone pair. this one has 2 bonds and 2 lone pairs. But let me do my silly cheerleader moves, and it'll probably stick with you better. Then we'll look at the simulation. Then I'll let you look at the chart, because I don't want to show you the chart right now, because then it just becomes names and numbers and memorization. Okay? Okay, 4 groups. Ready? I think I can get 109.5. We'll see. Okay, this is 4 things equally spaced in 3 dimensions. Okay, like that. So these 2 are in the same plane, and these 2 are in the same plane, and there's 109.5 degrees from one arm to the next, and from one leg to the next. But they're all perpendicular to each other. Or sorry, the 2 planes are perpendicular. So like, if you were to measure, I'm not going to tell you that angle because I don't want you to get confused. Any 2 bonds would be 109.5 away from each other. Because if I tried to like do this and make them all planar, now they actually would be 90 degrees. So doing it this direction allows them to have a little bit more space. Okay? So this is called tetrahedral. So tetra because there's 4, hedral because it would create a shape if you like took wherever the, how would you do that? I can't use my arm. So if you took this plane and created a side, you would, and do that on all the sides, you would create a shape. Okay, a hedral or a hedron. I'm getting tired there. Okay, so that's CF4. Tetrahedral electron geometry. All of them are bonds, so the molecular geometry looks identical. So it's also tetrahedral. Okay? NF3 also has 4 things, but one of them's a lone pair. So I'm back to this, but this guy's a lone pair. Now, this looks way better in the simulation because I can't tip myself on the side to show you what it looks like, so I'm going to show you in the simulation. The electron geometry is still called tetrahedral because I didn't change, I just went from this to this, right? It's the exact same arrangement, the angles are almost exactly the same, maybe a little bit squished because this is taking up more room. And the name comes from if you rotated me down so that my 2 legs and my arm were sort of near the floor. So I'll show you that one instead of trying to do it. Like this. Okay, so here's me standing, vertical, legs, arms, like this. Okay, if you tip it down like that, you can see really quickly that it looks like a pyramid. So it's a 3-sided pyramid. So trigonal for 3, pyramidal for pyramid. So hopefully you're seeing quickly, it would be really stupid to just look at the chart and just straight memorize them. If you can picture what they look like, it's going to help you to determine this whole idea of molecular polarity, but it's also going to be easier to remember the names. Okay, now the predicted bond angles are 109.5, but with that lone pair, they're going to be slightly squished. All I want you to say is less than 109.5. If you go to the real molecules, you can select one that's similar. I think they have NH3 in there. And I think that they say that the real angles are like 107 or 107.5. I don't care the exact number. Just know that they're less than 109.5. It's usually by like a degree or 2. Okay, last one. So still the same arrangement. This is water. 2 bonds. 2, I'm thinking anybody walking by is going to be like, what is going on in there? Okay, 2 bonds. Those are going to stay the same. Here's the 2 lone pairs. They're still tetrahedral, but they're like this, right? So don't look at my arms. They're influencing the shape. You can't just think of the 2 bonds. You have to know these are here. But the shape of my legs, that's bent, right? It looks almost identical to the bend we had before. The difference is the bend before was 120 degrees, And this vent is slightly smaller because I've got 2 pairs up here, and it's slightly less than 109.5. Okay, so they're still called vent because they look almost identical. Their angles are just a little bit different. The angle that comes from 3 groups is 120 or slightly less than 120. The angle that comes from 4 groups is less than 109.5. That one's pretty significant. It's like down to like 104 or 104.5. So 5 degrees that it loses because of those additional lone pairs. Okay, so let's do that on here. So another lone pair and losing a bond. So this is like, there we go. This is the way I was standing, right? And if I just twist it to the side, you can see it looks bent. The way I would want you guys to indicate the angle is just put 2 less than signs. So it's less than 109.5. It's just a good way to note that it's different than the one that had 1 lone pair. So I'll go back to the notes and put this in. Okay, so the angles here would be 109.5. This would be less than 109.5, and this would be less than 109.5. I promise it does actually matter. All of them, the electron geometry would be called tetrahedral. For the molecular geometry, this one was still called tetrahedral. 1 lone pair and 3 groups was trigonal planar. And 2 lone pairs and 2 bonds was bent. Those are the molecular geometries, but they still all share the same electron geometry. So when you're thinking about these things, I'm going to scroll down to the table in a second. When you're thinking about things, because we're going to add on 2 different ideas in chapter 11 in addition to this, as well as if you notice at the beginning of the notes, I said 2 days. So this chunk of notes is spread over 2 days. We have to do 5 and 6 groups, which sadly I won't be able to do with my body because I don't have that many appendages. So we'll do 5 and 6 groups later, and then we're going to talk about 2 different concepts that still rely on the number of groups. So literally the most important thing, the thing you have to think of first, is what is the total number of electron groups. Remembering that could be a single bond, a double bond, a triple bond, or a lone pair. Okay? Because like I said, there's 2 other properties that are going to rely on this. Okay. Who is confused, frustrated by the whole idea of polar molecules that you have to do for lab today or tomorrow? Is anyone freaking out about that? Really? Okay, there are people freaking out about that. So if you don't want to know yet, which maybe we don't want to know because it's not in the notes yet, maybe we just won't talk about it. But if anyone's like, oh yeah, I remember we have to mark those as polar and non-polar, then you can hang out for 5 minutes and I'll give you a brief rundown just as a courtesy to help you get through your lab assignment. Okay? Otherwise, we'll just be done now. Because it was a very brief overview and I think it would be confusing if I try to do it now. Okay? All right, that's it.